Hello everybody, my name is Philip Johnson. Today I'm going to discuss an experiment I conducted concerning an object falling downwards subject to Earth's gravitational field and a force I will describe called drag force. We'll discuss in order assumption for the experiment, such as participants in the model, choice of axes and timescale, motion observed in the experiment, and possible sources of error, the computational model of the experiment without and with drag force, comparison between the experiment and computational model without and with drag force, and the concept of terminal velocity. First, we will cover the assumptions for the experiment, such as the participants in the model, choice of axes, and timescale. In my experiment, I dropped a 40mm ping pong ball from above my head. I calibrated the tracker software based on the diameter of the ball, 0.044 meters, and captured frames of motion from release until the ball's contact with the ground. To make data reading easier, I fixed my axes such that the origin rested on the center of the ball and such that the ball is falling in the negative y direction. The timescale over which I measured the experiment was 0.734 seconds, captured in 0.033 frame chunks as per the 30 frames per second allowed by my camera. Let's move on to the motion observed in the experiment and possible sources of error. My ping pong ball starts at zero initial velocity. It was held at rest by my hands. Then I let go and the ball falls in the negative y direction. Note that at the end of the ball's trajectory is a light kind of variation in x position. There may have been a slight unintentional spin added to the ball, such that there is movement in the x direction as well. We can already predict some mismatch between our experiment and model based on that fact. Additionally, the ball fell at such a rate that it was difficult to pinpoint the true point of mass of the ball. Instead of a ball frame by frame, it was more of a blob. To keep consistent, I marked the middle of the sausage-shaped blob, but this may not be the most accurate point of mass. Let's move on to the computational model composed for the experiment that does not include drag force. Pretending that my ping pong ball was a superdense 2.7 grams, I edited Python code to model the case that the ball was subject only to the gravitational field of the Earth and subject to no other forces. I inserted the following conditions into the code. I had a system mass put into kilograms, I had a ball position of 0 and a ball velocity of 0, and I used a vector for the y-axis. In the while loop that uses Newton's second law to predict motion, we have the weight force equal to the ball mass times gravity times j hat, and then we set the F net equal to W because we're assuming no other forces are operating on the ball but this weight force. Using arrows to represent forces, note the yellow arrow representing the gravitational force exerted by the Earth. This model shows the object falling as fast as it can possibly fall. How does this compare to the actual experiment in which the ping pong ball is not superdense and is subject to drag force? We will see, but first let's discuss the computational model that does include drag force. Initial conditions are the same in the code, but this time we've added Ft equals negative b times magnitude of the ball's velocity times the ball's velocity, and Fnet equals W plus Fd. In this case, Fd represents drag force. B is a constant dependent upon the substance creating the drag force, in our case, air. To derive this constant, I adjusted the number until it matched the end of my data in the experiment. As such, we can then observe the middle of the data plot to see any discrepancies. By matching the b to the end of our data, we at least know that b is close to the value that the actual experiment had along the ball's travel. It's a decent approximation. Note when we run the code that we've added a blue arrow to represent drag force. It has the same arrow scale as gravity. Note how drag force increases over time as the ball travels. Collecting data from both models, let's explore the charts of experiment versus model that we produced, first looking at the case without drag force. The model with no semblance of drag force very poorly matches the experiment. This is not surprising. In addition to the inaccuracies explained earlier in the video, we dropped a ping pong ball. It is hollow and very flighty while traveling in the air. Its lack of density makes it much more likely to be subject to slowing down via drag force. Aside from the initial conditions, which are directly punched in to match with the model, every data point is far off base. Let's now look at the model with drag force. While still not perfect in matching the experiment, it's definitely better. This is because the graph takes into account air resistance, resistance to which the ping pong ball is likely heavily affected by. It is no surprise the beginning and the middle of my graph here matches the model. We punched in the numbers directly. There's no prediction even going on here. In the middle, where the graph still does not match very closely, this could be due to an inaccurate constant b, the possible spin I put on the ball earlier mentioned, and/or errors marking the point of mass and tracker. Last, we'll discuss the concept of terminal velocity. Pause the video to read the formal definition of terminal velocity if you need, but I'll just describe it in layman's terms. In layman's terms, the system is falling the same distance each time interval because that is as fast as it can fall given the conditions being the forces acting on it, such as drag. Did our ball reach its terminal velocity? You can observe the numbers for the ball's descent to see if it appears to reach a constant velocity. Terminal velocity is constant velocity, equal to as fast as an object can fall given the conditions it is subject to. The difference between the distances measured at the last couple of data points are very close, all around 0.13 to 0.15 meter difference. From this we conclude that it is possible that the ping pong ball was approaching its terminal velocity near the end of its descent on the account that it was not accelerating anymore. Part of the reason I dropped it from so high is to see if we could reach this terminal velocity. Note that the model without drag force cannot model the terminal velocity. Drag force is fundamental to the concept of terminal velocity. In the case of only gravity, the velocity increases indefinitely until the ball hits the ground. We could further investigate if terminal velocity is reached by applying a force to the ball initially. With an initial velocity, the ball should reach its terminal velocity faster, as terminal velocity is a limit on the speed at which the ball can travel. We run our code, watch the ball quickly descend, then look at the data. We have plugged an initial velocity of 10 in a negative y direction and adjusted the time step to be similar to tracker. As we can see, there's a difference of about 0.12 to 0.13 between data points. The ball seems to be approaching its terminal velocity, and it's doing so even sooner than in the actual experiment, confirming the notion that if initial force applied, an object will reach its terminal velocity sooner. This concludes my analysis of a ball falling subject to Earth's gravitational field and a drag force. Be nice when grading. Bye.